Okay, good afternoon and welcome, all of you here at the Brightland Smart Services campus and all of you watching from home or at the office. Today we are going to talk about a very exciting topic, at least as far as I'm concerned, the Einstein Telescope. My name is Martine Hermans and I am honored to guide you through the project today, or to this event. Honored, I actually mean that because we are going to talk about two of my favorite topics. So artificial intelligence in combination with the Einstein Telescope. And a little bit about the Einstein Telescope. I mean, we had Albert Einstein who predicted that there was something called gravitational waves, and Professor Hild will tell us all about what that is in a minute. And he predicted that in 1916, and it took us about 100 years to prove that he was right. And well, Professor Hild, who is with us today, was also part of the research team that discovered that. And now we want to know more. So now we want to build an even bigger and even more accurate research facility. And we want to do it here in this region, on the border of the Netherlands, of Belgium, and of Germany. And that is what we call the Einstein Telescope. We want to build it deep under the ground. And we will hear what that will look like and how it will work. And I say we want to because it's not certain that we will get it. We have competition, and the competition is Italy. So in 2024, we will know if it will be located here or in Italy. And then it will take quite some time to actually build it. But I think the lookout is very exciting to have such a, well, potentially such a very high impact research facility here. And it's not just research, as we will also hear today from René Kessen from LIOF and also from Roy from Boosting Alpha. It has a much wider impact in society and in business than just in the research community. So we're very excited here today to tell you all about that. There are preparations going on. It's a massive project, a massive undertaking. And one of the preparation projects is called the Einstein Telescope Technology Project. And that is what we're working on today. And we would like to show you what is happening there. This is the first session of in total 4 sessions in which we will catch you up on what is going on, because what is going on is pretty cool. So we would like to share that with all of you. And we would also like to invite you to think along and to ask questions or to come up with suggestions, things we might not have considered yet. So all of you here, but also all of you online, if you have any questions, you can type them in the chat function. I will get them here and we will answer and discuss as much as we can during this session. So to start, I would like to invite Professor Stefan Hild to the podium. He is Professor of Experimental Physics at the University of Maastricht. He's also the head of a research facility called the ET Pathfinder, in which we experiment with hardware that could be used to build the Einstein Telescope. And he will explain to us what is the Einstein Telescope, what are we trying to measure, and how are we trying to do that in the Einstein Technologies Project.
Yeah, thank you very much for the nice introduction. Welcome, everyone. As you heard, I have the pleasure today to talk a little bit about the Einstein Telescope, but mainly about this project, to give an introduction. What is ET Technologies? In particular, what are the work packages, in addition to what we will hear in much more detail later today. I just need to see how that works. Okay, so we heard already gravitational waves. Einstein predicted them, and we are really, really fascinated by the new window that we now have open to listen to the cosmos, listening to the mergers of black holes and neutron star, maybe in future even hearing stars blowing up, supernovae and things like that. And the key here is really to understand what is in the cosmos, what drives the cosmos, what are the forces in the cosmos. We know most of the energy in the universe is actually not consisting of matter and like us, like what we have in our hands and so on, but these terms dark energy, dark matter, 95% of the universe is made up of these, and we have very little idea what this is. And obviously, you know, as scientists, that's quite frustrating if you know that there's so much out you don't know. So this is really kind of, you know, the big picture, what we want to do with gravitational waves. So you're really just at the starting point here. Many people compare it to where Galileo was when, you know, he built up the first telescope and looked at the moons of Jupiter. Good, so that's the science pitch in all of this. And we had heard before, we want to build an Einstein telescope. So what's so special about the Einstein telescope? Right now we have some marvelous facilities, 3 to 4 kilometer big gravitational wave detectors, which were actually constructed in the 1990s. We are working on these for, I worked my entire career on these machines here, and these are marvelous. They brought us the first detection of gravitational waves, but the problem with them is they're really not sensitive enough for what we want to do. Yeah? So to give you an example, we want to start our next science run actually in February next year. Then we will switch these interferometers on there, and then for every week that we have these operational, we think we will hear about 1 second of a signal. And that is, yeah, it's nice. It's many, many more signals than the 100 years beforehand, but it's still not what you really want. So with the Einstein telescope, we want to have a game changer in here. And instead of occasionally hearing some signals over the noise, more or less you will hear signals all the time, millions of signals. And actually the challenge turns around. Rather than actually waiting for the few signals to arrive, you have too many signals, you need to disentangle them and so on. And that's obviously part I think we will hear a bit more about later today. Good, so that's the Einstein telescope, marvelous facility, and obviously lots of technology involved. And that's one part why we're here and why we're talking with industry. There's pushing technology on all different fronts if you want to build such a detector and if you want to analyze the data. Again, talking about, you know, collaborations with Boosting Alpha with the universities who do data analysis. I think we will hear a little bit more about this. But this is really why not only scientists get interested about this, but why we have LEOF, you know, the government engaging in many, many companies. And that's super useful because also we couldn't build it on our own. Yeah? Scientists can build small stuff in the lab, but scientists are not going to build a €2 billion facility underground and stuff like this. So a very useful synergy here. Why are we so interested in the Einstein telescope? I mentioned a few of these points. It's really kind of, you know, all of these new technologies give you kind of, you know, this innovation radiating out into industry, attracting people, educating the next generation of scientists. But then, you know, we see it from the people we have in universities. Most of them go to ASML and to other companies and actually help the economy. And this is really kind of what drives us here to have the Einstein telescope actually quite nice close by here. Good. In order to get to that, there's now quite a big ecosystem that has been built up here in the region with different projects. A few were mentioned already. We started off, I think the first one was ET Pathfinder, where we have a small version of the Einstein telescope to test technology in a very similar environment to the Einstein telescope and at the incredible sensitivity. There's eTest, EMR. This is testing 2 different sets of things. One is about the geology, mapping the geology. Where do you actually build this? How does it work with underground and so on? And the other one is testing a particular cooling technique for silicon mirrors in there. We have ETs to SME, and you see there the collaboration with the industry is really in the foreground, where small companies can actually work across the border, get vouchers for certain technologies to develop these. And actually one of our partners here, I think JPE, for example, who is also an ETT, is actually one of the recipients of such a voucher to develop a new device. Then we have ET technologies. We'll talk about this more. There's a national growth funds, 42 million again for development of the ecosystem, working with industry, but also the underground. And then there are more European ones where we set up the project office for the Einstein telescope. So obviously we are always working on 2 different fronts here. We heard it, we want to host the Einstein telescope here. So that's obviously one circle in which we work and so on. But as a scientist, I also work on the other front. The much bigger front is obviously we want to have one Einstein telescope in Europe. And that's obviously also something where we actually help developing this. And then there are things like the Dutch Black Hole Consortium. So quite a big ecosystem which covers all the different aspects, some of them more focused on the region, some of them more focused on the European thing, but all hopefully trying to push forward that we soon will have an Einstein telescope. So now we come to ET technologies. what are the main purpose of this particular part of the ecosystem. And here we want to do two things, which we have here, two main objectives. One is developing and improving technologies. Yeah? There are certain things, if we talk about vacuum system, infrastructure, underground, and so on, where really, and many of the cryogenic technologies, where really the biggest skills are actually not only in research institutions, but also at industry, and obviously want to profit from the synergy. So this is really kind of making the Einstein Telescope possible, technologies better. And at the same time, while working together, we can actually boost the regional economy, prepare actually companies to understand, what is actually needed to then, when the big investments come, being in a very good position to bid for this money. So these are more or less the two objectives. And then this is focused in 6, there's also an organizational work package, but 6 real topic work packages I will quickly go through. And I have to say, it's quite fascinating. I was saying to someone earlier today, I don't think I've ever been part of a project which is so diverse in terms of the range of topics, but also in the approaches that people do in different work packages. Some are very much focused on a very narrow task. Others are much wider to look at what is actually possible and really kind of scoping out, and it's a little bit, it's not clear where the journey will go and so on. So actually quite interesting to see this. So what are we doing? So on the cryogenic side, and I always put the companies and the institutions here in the upper right corner, this one which applies mainly to ET Pathfinder, where we want to learn with CryoWorld, with JPE, how to actually cool a mirror in a very stable way. Yeah? For these gravitational wave detectors, you need to have very quiet mirrors. If you connect them to a cooling system always does noise. So the question is, how can you, in between, find either a way that the noise from the cooling system is not transmitted, or that in between you have things you actively control and stabilize to keep them quiet. And this is what we do actually in this work package 1. For work package 2, we are thinking about the vacuum system. So the Einstein Telescope, as it's designed right now, will require 120 kilometers of vacuum tube. It will be the largest vacuum system in the world. And there are funny comparisons if you just scale how these 3 and 4 kilometer detectors were built, and you do it at the same speed and so on, then just the construction of the vacuum system for ET would take 25 years, okay? And that's obviously something that you don't want to have here. You need to do this more efficient. You want to save money and so on. And there are quite a lot of interesting techniques how to make it maybe cheaper by using different types of steel, applying certain coatings to protect the system, but also to improve its performance in vacuum. And here NICEF has teamed up together with a steel producer, Tata, and VDL, who obviously do quite a lot of this processing, controlling, and detailed planning. Work package 3 is InnoSize, which is a spin-off company from NICEF, which does sensors to measure what vibrations are there in the ground. So they have very nice seismometers that we actually use in campaigns all over the place, and also in the current detectors. But they now want to look at a gravity gradient sensor, so to look at how the field changes over space. And that's something which is quite hard actually to measure, and there are some clever ideas how to actually do this, and that is currently explored in this work package. Work package 4, again, you see we're jumping all over the place. It's very, very different topics. Work package 4 is NICEF and Oracle Netherlands. So this is kind of using satellite data and some clever, actually, I think patented protected algorithms to use surface data. So you scan the surface with a satellite, the height and so on, and from that actually predict the underground structure rather than having to go and drill holes and take the cores out and so on. They have some magical ways to give you information what happens there, water flows and so on, stability. And we are currently looking into this, and I hope over the next few months we will see the first results, what you can actually learn with these magic technologies. Work package 5, I will keep very short because I think that's something where we want to hear more later today. It's really kind of just to understand there's lots and lots of interesting algorithms out there to do in a classical way data analysis or classical trading. And I'm pretty sure there are many, many more clever algorithms out there, whether it's networks or whatever neural parts you have. And that will be quite interesting to understand how you can improve, or if you can improve with them, gravitational wave data analysis, where data analysis, just to be clear, always means two parts. In the past, we were mainly after finding a signal in there, but now the computational power is mainly in this part of, once I have my signal, I want to learn about the physics from the object, where does it come from, and that is obviously a slightly different challenge in here, but I think there are useful applications for both of these. And then the final work package, actually led by Rob, who is here today, is about sustainability in the widest sense of sustainability, not only the ecological thing, but also about kind of, how can we make effects of the positive effects of the Einstein Telescope will have a lasting imprint on the region here. So it's really kind of, about the economic impact, as well as kind of the, quite a lot is obviously environmental impact. If we think about this nice region here, what do you do with all of the stuff you take out of the tunnels? Where do you put it? How do you get it away without building a motorway here to get it actually out of the way? What happens about water management? If you actually build something underground, you probably need to pump water away, which otherwise would get into your tunnels. What does it do to the water levels here? The water that you collect, you probably have to put somewhere up again. Can you just put it into the river? There's quite a lot of interesting aspects here that we need to think about, and the whole topic of energy and so on. Good. And I think with that, I thank you, but in particular, I thank also everybody who sponsors this project and who made this project possible, and in particular, all of the partners. And as I said, I hope that was okay to give you really a kind of a top-level overview. It's a very diverse project, and about each of these work packages, I think we can talk for half an hour if people want. And I hope at coffee we'll have some occasion for that. But today, obviously, it's all about the work package 5, and I'm curious to hear what people have thoughts on these technologies. Thank you very much.
Thank you very much, Professor Stefan Hild. Are there any questions?
Yes. Thank you for a nice explanation. I was wondering which of the aspects of all this technological development. Sorry. I was wondering which of the aspects of all the technological developments will actually make the resolution or the sensitivity so much better than the other existing telescopes.
I think there's two different aspects here. One is actually that at the moment all gravitational wave detectors are built to cover a whole frequency range. So like if you think about light, the whole color space and so on. While we now already know from astronomy, it's much easier. If you think about astronomy right now, you have completely different telescopes for X-rays, for optical light, for infrared light and so on. And the same we are trying to do with the Einstein Telescope. So one thing is to say, instead of building one interferometer to cover all of the frequency range, you split it into two, build a so-called xylophone, and that gives you already quite a lot of sensitivity, because you have different noise sources which dominate different parts that you can actually in your spectrum, and that helps a lot. And the other biggest thing I think is that we go cryogenic, that one of the limiting noise sources is that everything wobbles what has temperature. In particular, your mirrors, the elements from which you hang your mirrors and so on. And by cooling that to minus 250 centigrade, that I think will give you another big improvement. And then there's another 10,000 small things, but I think these are two of the biggest ones, I would say.
Thank you. Any more questions? No? Thank you, Professor. Then we move on to our second presentation of today, which is by René Kessen from LIOF. He works as a business developer, and he will talk a little bit more about linking this seemingly very scientific endeavor to industry and to businesses, particularly small businesses, and how we can benefit actually economically also as a region and the businesses in the region from this Einstein telescope. René, you have.
Thank you, Martine. Thank you. As Professor Stefan Hild already mentioned, there's a lot of things going on already in the context of the Einstein Telescope. And the decision for the location still has to be made in a few years, but as we speak, there are a lot of developments already going on, a lot of technology developments going on, and a lot of opportunities are included in these developments. But these opportunities, business opportunities, they don't reveal themselves by themselves. They don't develop themselves by themselves. And this is why in 2021, 7 partners in the region they cooperated and set up a project to build a bridge between the technological and the business opportunities on one side and the companies in the region on the other side. And this is what's called the project ET to SMEs, which started in March 2021. My name is René Kessen. I work as a business developer for LIOF, and LIOF is one of the project partners in project ET to SMEs, and it's also the project partner in the Dutch region of the Interreg EMR region, where this project will take place. Now, what I'm going to talk to you is about, let's say, the summary of this project, what we do in this project, and also what are the goals of this project and how we approach that. Our targets is to include and involve all the companies in the region, EMR, in the developments that are already happening at Pathfinder, at eTest, and all other projects, and help them to find the business opportunities specifically for their business. And what we also want to stimulate is cross-border collaboration between companies, between research institutes and universities, SMEs and large companies cross-border in this region, and to, let's say, to grab the opportunities hidden in these developments. And what we also would like to emphasize is that the developments in the Einstein Telescope, they are not just to use within the framework of the Einstein Telescope. All the products involved in the Einstein Telescope, all the technologies development, they also can be applied in other markets. There is only one big Einstein Telescope later, so the volumes for the Einstein Telescope market is not that much. But if you can apply this technology or product in other markets like automotive or aerospace, then these are significantly larger markets, and also the business case is of course then much more interesting. Now, to create this bridge between both worlds, we have set up a complete value chain that consists of 4 big steps. We have the mapping as one step, we have business development support as the second step, attractive fundings as the third step, and sustaining as the fourth step. And in this presentation I will guide you through all these 4 steps. Now, the first step, the mapping part, is what we did there, like in the project ETT, we also have, let's say, defined 12 technology domains that are relevant in this Einstein Telescope framework. And these 12 consists of 8 for the instrument itself, and 4 for everything that has to do with the underground and the infrastructure. And this technology catalog is on our website, ET2SMEs. And if you, for example, click on cryogenics, then you get a whole worksheet, a whole paper on this specific technology, and it describes what are the challenges in the Einstein Telescope context, what is the current state of the art, what are potential other markets for this technology, and this is done for all of the technology domains that are in this catalog. Now, what's also in the mapping tool, we try to create a map where all the relevant players in this Einstein Telescope, where they are active. And these are companies, these are research institutes, these are universities, large companies, SMEs. And for every partner involved, we have made a profile that describes who is the company, what is their core business, and what is the link with the Einstein Telescope. And so far we have created a map with already more than 300 relevant actors in this framework of Einstein Telescope. And of course they're not all the same involved in this framework. The other company has more, let's say, more connection to the Einstein Telescope than the other one. This is the exercise that we do to explore with each company that is interested, okay, where is the opportunity for you in this project? The second part of our approach is the business development support. Now, what we have done in the beginning of a project, we have sent out a survey over all of our networks in the region, informing companies about the Einstein Telescope, what will happen and what is already happening. And we ask them basically the simple question, are you interested in developing or discovering the opportunities for you in this project? And based on the response, we have conducted company visits. With each company that expressed this interest, we sat together, we got to know the companies, we explained what is happening in the Einstein Telescope, and looking at their current business and their products and their technologies, we try to discover, okay, what would be the connection with your company in this project, and where and which way you can benefit for everything that is happening in this project. And so far, within the region, we have visited 217 companies. The visits are still ongoing and will be ongoing during the course of the project. And what we also did is we connected the companies to the specific technologies that we defined. And so far, 344 competences were related to the Einstein Telescope catalog. Now, what we also did, you have to tell the story, of course. A lot of people, when we started this project, and actually nowadays it's still the case, many people have not ever heard of the Einstein Telescope. If you talk to people, businesses today, some people say, Einstein Telescope, what's that? So you have to inform them about what is the Einstein Telescope. And what we also do is to, let's say, to be visible in, for example, fairs or exhibitions, where we participate as a project team, either by visiting the event and spreading the word there, or by participating with a booth. For example, we attended the Precision Beurs in Sertogenbos last year. We will do the same this year, and we also visited relevant technology-related events, technologies that are somehow related to the Einstein Telescope. And we also invite companies, let's say, to discover the possibilities, the opportunities of the Einstein Telescope there. What we also did in this work package is we organized some online and physical workshops. We had planned to conduct 6 physical workshops, originally end of last year, but for apparent reasons they could not take place. So we decided to have 2 online events on instrument technologies and on geology technologies. And we moved the physical workshops to the period April until June of this year. So we had 6 workshops, also a bit divided over the different technologies. And actually the last workshop was last Tuesday, and there we not focused on the Einstein Telescope technologies, but we focused more on what it takes to, let's say, to keep the Einstein Telescope running for the next 50 years once the start button is switched. And we focus there on maintenance, on health and safety, and also energy supply and water management. Now, the third step in our project is that we have attractive fundings. And if, as a company, you see the opportunity to develop a product or a process or a technology that is somehow related to the Einstein Telescope, and you also have a partner in the region, cross-border, that wants to collaborate with you, to fill a certain competence gap, or to, let's say, to add some expertise, then you can apply for an innovation voucher that, let's say, takes away the first risks, the first costs of this innovation project. And we have grants up to 50,000 euros to support this innovation project with a lead time of up to 9 months. Now, what's important is that this collaboration has a minimum of 2 companies, cross-border, of which at least one is an SME. The other one can be an SME or can also be a larger company. And additionally, beside those 2 companies, you can also have research institutes, universities, or whatsoever involved in this project as a partner, as a supplier. Now, we already had 5 calls where applications can be submitted. And the next call, the sixth call in this program, opens on August the 1st and closes on August the 29th of this year. Now, if you look at these innovation projects, I already mentioned that we challenge companies not just to look at the Einstein Telescope as a potential market, but also look at current markets, other markets, where you can use this product or this technology. And what helps is that the technologies in Einstein Telescope, they perfectly fit within the key enabling technologies that we have defined here. So if you look at the instrument technologies, they perfectly match within all the areas of the key enabling technologies, and also the geology technologies, they can be divided somewhere over these areas. So other potential markets could be astronomy, Einstein Telescope, but also aerospace and other more automotive, and also other relevant markets that you can see as potential interesting for this project. Now, how we approach this with companies that have a certain project idea, they contact us. They give us a call, they send us a mail, and they say, okay, I have this project idea, and I would like to see what's possible. And at that time, it's just an idea. So what we do there is we help the companies to define this project idea in a 5-step, let's say, format. So that starts with, okay, who are you and what are you doing right now? What is the project idea? What is the innovativeness? What is the link to the Einstein Telescope? And what kind of partner do you need in this project? What kind of competence are you looking for? Now, after this, they filled in this format, we will discuss this project idea in our business development team, and that consists of business developers from the 7 participating partners. And then we're going to look in the other regions, what potential companies, what potential partners can be found, can be linked to this competence, to this expertise that is needed by in this project idea. And if we have a match, then we arrange introduction meetings where the companies can get to know each other, they can discuss the project idea, and then during this meeting there will be a yes or no, a first match. Okay, there's some chemistry going on, and there is indeed a technology match and a competence match, and that is basically the start of let's say further development of the project and of the collaboration. And if the project is defined and if the application is ready, then they can submit the application for a call in the voucher scheme. Now, the business developers in this project, we have 3 on the German side, we have 1 in Walloon, 3 in Flanders, and 1 in the Netherlands. So we invite the companies in this region, please contact your business developer if you have a project idea, if you have been inspired by the opportunities in this Einstein Telescope framework and you want to really grab these opportunities. The last step is what we call sustaining. Of course, it's an Interreg project and it has an end date. And we certainly do not want that all the activities, all the achievements that we have achieved in this project will end at this end date. So we're taking care that all the things created, they continue after our project has ended. And one of the examples is that we have set up an industrial advisory board together with the project ET Pathfinder and the project eTest, where scientists and companies meet physically or perhaps online to discuss opportunities, to discuss technology developments, and to let's say to find each other. And not just the scientists and the companies, but also the companies located cross-border. There are a lot of interesting matches already made between companies from one side of the border and companies on the other side of the border that decided to collaborate also outside the Einstein Telescope context. So it's really a good platform to expand your international network, and especially in the region. Now, if you want to have more information, my name was here on the right side as a business developer, but you can also see some information on the website et2smes.eu. We also have some promotional material. Communication is also one part of the project package. And yeah, this is the, let's say, these are the 7 partners that are included in the project. We also have a few associated partners that help us finding companies, approaching companies located in the different areas. We also have partners that really supported our project, and they wrote a letter of support, letter of intent by the application of the project ET to SMEs. And of course, a final word for our sponsors in this project, Interrecht, and also some parties within the region. And that is, in a nutshell, what I want to talk about the project ET to SMEs. And of course, if you have any questions or remarks, now is the chance. Thank you.
Thank you very much, René. I see already one question.
So when a knowledge institution participates to this project, how does it work in terms of funding? So the funding goes to the SMEs, and the the research institution can participate, or also the research institution gets funding out of this schema?
Yes, good question. The project that we do, we are subjected to the European rules on funding, and these rules say, in this case, that we can only fund the SMEs that want to innovate. We have collaborations between SMEs and larger companies, and in this particular case, the developments are also interesting for the larger company, not in terms of funding, but for, let's say, for a long-term strategy. They can use the things that are developed in this project for other purposes as well, rather than just this project. And the same also applies for research institutes that are involved in this project.
Thank you. Any more questions? No? Thank you very much, René.
You're welcome.
We received a couple of questions through the chat, and I would like to. I think these are more for Stefan still. So maybe we can take a few minutes to answer them shortly, and then we will take a short break. So one of the questions is: many of the partners currently are Dutch organizations. The question is: will there be any international collaborations, for example, with MIT or with CERN?
Yeah, very good question. So there are collaborations. So we, as I said, it comes back to this kind of thinking about the different spheres. So the Einstein Telescope is a scientific project which covers all countries in Europe, about 1,200 scientists in Europe. Also has kind of a sister project in the US called Cosmic Explorer, and there, for example, we interact quite closely with people, Caltech and MIT and so on. So I think that, and actually there are partners in the Einstein Telescope which are also from Japan and from Australia, so that is not anything that is closed or so. Yeah, so that everybody is welcome. CERN is a slightly different thing. So we have some MOUs, and we are now starting up a few different collaborations on certain topics. So for example, the vacuum system is something where now the ET collaboration has made an MOU with CERN, and CERN will develop the long beam pipes together, for example, with partners here from Work Package 2, I think, and so on. So there will be also interactions with CERN, because CERN obviously has a very long history in quality control, making big science projects actually work. So it's a win-win situation, and yeah, we're collaborating with them.
Thank you very much. Last question. Will you or do you work together with the Event Horizon Telescope team or any other teams or events that work in black holes and the results that come out of that?
Yes, I think we are collaborating. I mean, for example, me personally, we collaborate with a group at Radboud University, Heino Falke, who is one of the brains behind the Einstein Telescope, and we are writing grants together and so on. So these collaborations happen, and whoever has, I mean, the last few years have shown us with this dawn of multi-messenger astronomy, where we saw the neutron star merger, where then, we learned quite a lot of this event after the gamma ray telescopes and the gravitational waves that, so to say, triggered the astronomy community. Then more or less in all different parts of the astronomy community and different spectra, people started to observe this event, and we saw how much you know, how much information you can get out of this. So there's huge synergies, and yes, whoever is interested in collaborating on black holes, I think we are very happy with it.
Thank you very much. Then we will take a 10-minute break. We will start again at 3 o'clock. For everyone who's watching online, please feel free to also get a cup of coffee and keep the questions coming. We will return after 10 minutes.
Test, test.
All right, welcome back, everyone. So we will continue with our program, and we will now move to work package 5, as earlier explained by Professor Hild, which is the work package about artificial intelligence. And we will look at it from 2 angles. So this work package is a collaboration between the Open University, the University of Utrecht and NICEF, and Boosting Alpha, which is a financial trading company located in Venlo. So it's also a collaboration between industry and the academia. And we will first hear from Lyana Curier, who is an assistant professor at the Open University, from a scientific perspective, what we're trying to discover with the help of AI in combination with gravitational waves research. Lyana, the floor is yours.
Thank you. Just to have an idea, before coming here, who had an idea of what is AI? You have heard about it, but can you define it? And who knows about the gravitational wave? Okay, just to know a little bit. So, as Martine has said, I'm Lyana. I'm a Earth observation scientist working at Open University. And today, it's one of the first presentation in about the work package 5, where we are trying to deploy tools for detecting gravitational wave and get ready for when the Einstein Telescope data will be there. So, as Martine has said, the work package is a collaboration between 3 sorts of expertise. Expertise from the gravitational wave, so the physicist from the Open University and NICEF. Expertise on anomaly detection from Boosting Alpha, but I will let Roy talk about that in the second part of the talk. And expertise on signal processing and deep learning from Open University. And what we are trying to do is that we are trying to develop tools to find unknown signal in existing data set, but we are also trying to, using the current gravitational detectors and deep learning techniques, create a synthetic data set which will look like how we expect the Einstein Telescope data to look like. So, just to give you an idea, and under the control of Professor Hild, gravitational waves actually are rippers in the otherwise tough and stiff space-time fabric. And what happened is that those rippers are caused by really violent phenomena which happen in the cosmos. So you can think in terms of colliding black holes, exploding stars, or even the birth of the universe itself. The problem is that when we think of the detector of nowadays, which were built in the 90s, some of you were not even born yet, we can think that the technology was not far advanced yet, so the data, the amplitude of those astrophysical events barely pass the background noise of the detector. So the gravitational wave that we are observing right now are swamped in the noise, in the background noise. And what happened is that in terms of signal processing, what we do is that we do much filtering. So we are trying to find the signal into the noise. So I tried to put it, I tried to trivialize it, but let's say that we have a noisy signal like that. We create a bank of templates, and then we are going to compare our templates to our observation, and we evaluate what we call cross-correlation, where we try to look for significant matches. If we think that we have a significant match, we say that we have detected an event. And the cause of the event is actually going to be determined by which template was used to identify, so we say. But to give you an idea, if we think of my voice, that's also a wave. So we are thinking of a wave which is going to in a room like that. If you have a room like that which is quiet, trying to identify my voice, is okay. It's a little bit of work, but you can do it. If I'm standing in a room, aula auditorium of aula PhD defense, become a little bit more difficult to pick up my single voice into, and to figure out that I am the one. Once you have detected the signal, to figure out that I am the one talking, it's even more difficult. Imagine that I'm standing in the middle of a BTS concert. That's what is happening. That's what we are trying to do. So it's work which is tedious, time-consuming, and computationally heavy. So what we are trying to do is that we are saying, what can we use, what can we do to detect and to have a more serene and parent time pipeline to detect gravitational wave. You see me coming, huh? What we want, and I will paraphrase Alan Turing, is that we want a machine which can learn from experience. So we want something which is going to learn by itself to pick up the characteristic and the feature of the signal. So this is called machine learning. This is a part of artificial intelligence. And we are actually even using a subset of machine learning, which is called deep learning, where we look into neural networks which actually are trying to mimic and to learn, but in really the human sense that you think of. So it's trying to mimic the process which is happening in the neocortex of human. So when you think of learning as a child or something, this is what we are trying to do. Apparently, Google succeeded. There is a sentient AI over there. I don't know if you saw the headline. Anyway, all that to say to you that we have reached a world now where the new industrial revolution is actually driven by data. It is a data-driven revolution where you look into artificial neural network. And when we think of serendipity, what we see is that by the time that machine learning, deep learning, has been starting since the 50s. But by the time that we started to have computational power to be able to do that, was actually the same time where we were being able to detect with the technology the first gravitational wave. Have you heard of deepfake? Yeah. Actually, I want to talk a little bit about deepfake because, believe it or not, deepfake is using techniques that we are going to use in this work package. And I say we. I'm not doing anything. The PhD student, Stefano, Tom, Melissa, those are the ones really doing the work. And actually what they are doing is that they are using something that we call GANs, Generative Adversarial Network, where it's a technique where you use two networks, and one is called a discriminator, the other one is called a generator. And the generator, what it does is that from a bank of data that we call the training set that you give him, is going to learn about the statistical feature of the data and is going to be able to generate new data. The first deepfake was, for example, Tom Cruise appearing somewhere he had never been to. That's what is happening. So you learn from data, photograph, data from interferometers, spectrogram, Q-grams. You learn statistical parameters, and then you generate new data. And what you do is that you feed those data to the second network, which is called a discriminator, and you try to fool him to think that those are real data. And if that works, then you have created a good network which is able to generate new data. So if we are able to do that, that means that if we take the observation that we have currently and we are able to generate that, that means that we can do different things. We can do data quality improvement because we can generate new noise. we can generate what they call glitch or blips, which are transient noise which comes. So we know how to do them. So it's easier for us to just create a bank of those glitches and to provide them to the scientist. You can also use it for creating the gravitational waveform. The gravitational waveform are basically the template I mentioned before, where using the theory, let's see, simplify it like that, you can create exactly how an astrophysical event would look like. Problem is that it's computationally heavy. It's not something that you can, simulation that you can run so easily. But if you train a network to be able to do that, then it might take some time to train it. But once it's trained, you can easily deploy it. The other way, it's also simply for gravitational signal search. So for example, there are teams right now which are looking into using neuronal network to identify CBC when two black body coalesce, so they form one, so they are trying to look for that in the data. And something that Professor Hild mentioned before also, where you're not solely interested in identifying those of observing wave. You want to know what is before, what is the source. And this is also where deep learning can help you, because they can help you to interpret what was the origin, what was the source of the gravitational waves that you are observing. So now what is happening is that in this work package, we have a few students, so Stefano, which is sitting there, Melissa, which I think joined online, which are looking into harnessing the power of the GANs, so harnessing what you know are deep fakes to characterize and generate new population of glitches and blips. And we have Tom, for example, which is looking at the same technique, but looking into new architecture to be able to generate artificial collision population. And that's just a teaser. Because in November, today it was really to get you acquainted with what we do and for a more general audience, but in November we will have a more in-depth presentation where they will have the opportunity to really present to you in depth each of those applications. And I really hope that I will see you and that you will also spread the word that this is an opportunity. That's about all I had to say to you today.
Thank you very much, Lyana. Are there any questions for Lyana? Yes, one question. Give me a moment and come to you.
Yes, where can we register for this event in November?
You the same way as now, you will receive. We will advertise it. Sorry, and you will get a link and you can register.
Okay, thank you.
One question, you said you're able to create new data sets for ET, kind of, I assume in the context of mock data challenges and so on. So that means you take, so what exactly does it mean? You take Gaussian noise and then the part is you put these blips and glitches that you created in there, or do you also create do something to the Gaussian noise that you use?
No, at the moment, it's just started, so they are really just developing and training the algorithm to be able to train it. But ideally, the idea it would be to be able to do a little bit like what we do in the satellite world, to do observing simulation system experiment, where you take contact with the hardware people and then they discuss about the project specification. And then you can create really specific data. So I think at some point, Tom will contact you or the other member of the VP, so we know exactly what are the current achievements, and that we can use as a PSD for creating really realistic data set. But we really just started in January, so.
If I can add something on that, we're also working within DET collaboration. There is a mock data challenge going on now. And and this is actually something that okay, so yeah, we are part of that, and we'll probably use the package that we're developing for injecting glitches in there. Yeah.
Yeah.
Any more questions? No? Then thank you very much, Lyana.
You're welcome.
So we got a little bit more technical there. For those of you who want it even more technical, we would we invite you to join the session in November. But for this session, we would like to conclude with what in academic terms we call valorization. And valorization is basically everything that we achieve in the world of science also has an application outside of the university. And in this specific work package, we have one company called Boosting Alpha, who is not only learning from us, but also we are learning from them. Because Roy Lenders is here, and Roy is the Chief Technology Officer of Boosting Alpha. Roy is a successful entrepreneur, has had many AI-driven startups in the past. And at Boosting Alpha, he, together with his team, is working on trading algorithms for financial markets. And those are actually very advanced. And it turns out that even in the world of physics, we can learn from each other. So the financial trading algorithms have an inspiring effect on the scientists, and also the science that's going on has an inspiring effect on Boosting Alpha, which is why they're in this work package. So we didn't want to keep that from you also today, to show you real life application and how they are using it. So Roy, the stage is yours.
Okay, thanks Martine. I'm going to, my name is Roy Lenders, Chief Technology Officer of Boosting Alpha. So what we do is we specialize financial markets, and we build basically complex trading algorithms that try to find patterns to make money. All right, so that's what's happening. Why do we do that, and why is it so difficult? Because everybody knows, everybody has probably experience with equity or forex. You're trying to predict the stock price, but one thing is for sure in financial markets: whatever happens has happened in history will never repeat again into the future. So that makes it quite difficult to predict financial markets. And it also makes it quite difficult to apply artificial intelligence, because you know that the data on which you train is never going to be the data of the future, right? So let me see how this works. Yeah. So what we specialize in, basically artificial intelligence, quantitative finance, algorithmic trading. We use both financial data but also non-financial data. So think about algorithms that trade based on Twitter feeds. We can use all kinds of different data sources. So what are we trying to solve? Basically, in the world of financial trading, there's many hedge funds, there's many investment managers, and every year there are reports being done of all the hedge funds in the world, basically, and everybody is trying to beat the market, right? But if you look at, in reality, how many hedge funds can actually beat the market, it's very low. It's roughly 5% of investment managers and hedge funds can actually have the capability to beat the market. The rest is basically, if the Nasdaq goes up 15% and your fund goes up with 12%, yeah, you could have better invested 100% of your money in the Standard & Poor, basically, and not in a hedge fund, because they made a lot of trades, but apparently the benefit from those trades were, yeah, you lost money, basically. So that's what we're trying to do. So a little bit about our company. We started in June 2018, and basically we focus on building the algorithms only. So we don't bring them to market. So we work together with B2B partners that actually use our algorithms and sell them to market. One of the partners is, for example, the Bots platform. You've probably seen them on TV with ads. They're very active with marketing. They're actually trying to be a unicorn end of this year. It's a startup from Haarlem. And roughly 60% of all the algorithms on that platform, we are the biggest trading algorithm provider. So that's what we do. But we also work with Coinmerse here in the Netherlands, which is a big crypto exchange, with Beurspro, with Mercor in Israel, Signally in the US. So we were active with many different partners. Yeah. So what are we trying to do? So we collect historic data from financial markets. And let's compare ourselves with a manual trader. If you are a manual trader and you look at these stock charts, these financial charts, and then people try to predict, okay, is it going up or going down, right? And I meet a lot of manual traders. And sometimes manual traders that I meet that have devised this intelligent strategy, right? And with taking these signals, and they made 100% in 6 months. That can happen, right? Those people exist. I actually met them. They made 1000% in 6 months. But they think that they can repeat that in the next 3 months. And once somebody is successful, they want to earn more, so they always raise the stakes. But sometime down the road, after 9 months, they go bankrupt. That's what usually happens. And why is that happen? Because a manual trader cannot test his strategy on history, right? He just starts, and he does things on feeling, but he's not 100% sure that it actually works. And what we do with algorithms, we actually test our algorithms on 20 years, 30 years of history. So we properly test our algorithms on good times, on bad times, on stable times, on all the different types of market environments that you can actually happen. We try to test our algorithms to see how stable are they. You know, how do they do in different market environments? And we also test live. So usually when we test it on history and we have a good idea, okay, it's stable enough, it's good enough, this will, you know, endure the test of live data. Then we put them also 3 months on shadow trading. So 3 months on live data operating to see, okay, is this really, you know, did we not overtrain it? Does it really work? And then we basically start with real money. So what are we doing in this project? We are crazy guys, right? So we test a lot of crazy stuff. And we are very experienced with AI. So one of the things we are bringing, I think, hopefully in this project, is that we help the teams from Utrecht University and Open University with some ideas on how you could apply AI to gravitational wave detection. But what we are primarily interested in ourselves as well is, can we piggyback? Okay? Can we learn some techniques that are used in gravitational wave detection that we can actually apply on financial markets? And when we started this project, we thought there would be 2 big interesting themes for us. One of them is using data from multiple exchanges. Why do we think that's an interesting idea? Because the current gravitational wave detection, as Stefan shown already, they use data from 3 different detectors. Why do they do that? Because those 3 detectors are spread across the world. So suppose a signal is only picked up by one of the 3, then it's probably noise, right? Because if it's a real signal, it would have been picked up by all 3. That increases the confidence in the signal, basically. And that's the same for us, right? Because many financial assets are not traded on one exchange. They are traded on different exchanges. Could be one in the US, one in China. Could be different volume, different market participants, whatever. So one of the things we are always looking is, can we find discrepancies, right? Discrepancies which are non-logical. So, and that means we can benefit from it, right? So the other technique that is interesting for us, the gravitational wave detection team is looking for what they call unmodeled searches. They're looking for signals they've never seen before, so they don't know how it looks like, right? If I'm looking for the Big Bang, for example, in the Einstein Telescope, nobody saw the Big Bang yet, right? So how does it look like? And we are trying to do the same thing on financial markets. We are looking for patterns, but we don't know which patterns, right? So that is an interesting area for us as well. So what are we concretely doing? Around this multiple exchanges thing, so we have Gregors here in the room. So what we have been collecting, and that's basically live since March this year, is from 3 different exchanges: Binance, Kraken, and Coinbase. Those are 3 of the biggest crypto exchanges. Binance is primarily Asia, Kraken is US, and Coinbase is also US. And we collect every single trade and every single change in the order book. So whenever somebody in the world places an order, we collect it. So it has been running since March. So we're talking about terabytes of data that has been collected so far, huge data volumes. And what we have been exploring is if we compare this data on exactly the same time frames, do we see differences, right? Because if we see differences, for example, for the price of the Bitcoin, if the price on Binance is 1% different from the price of Coinbase, that's a big topic, right? 1% is big. With one trade, we could earn 1%. And you would say, okay, the price is not 1% different. Because Bitcoin is a heavily traded asset with a lot of volume. But yes, we've seen occasions already where prices are 1% different for exactly the same financial asset. Now, I'm talking about crypto, but Shell, for example, Shell is traded on the AEX and in London. Exactly the same underlying asset, but the prices could be different, right? So basically, because the underlying asset is exactly the same, you could make money without any risk. And that's obviously what we try to get, right? We try to find discrepancies, make money without risk. Yeah, so that's what the other thing we are trying to do is, if we combine the signals from all three, could we, by combining the signals, could we create a higher resolution of the data by combining the signals and reducing local noise, right? Because we might have trades that only happened on, I don't know, Binance, which did not happen. Did not happen in the other exchanges, so you could say it's local noise, which did not get replicated to the other exchanges. So what we're also trying to do is, if we combine data from multiple exchanges, create a new data set with less noise, and then run all traditional algorithms, because then you get better quality data, basically, as input for the trading algorithms. That's obviously a little bit more difficult technique, so we are trying a lot of stuff, like GANs, genetic algorithms, autoencoders, and trying to figure out, we're working on this project together with the University of Maastricht, so we're also working with some professors, trying to figure out techniques, how we can combine data from multiple different places to basically get to a higher quality data format. The other one, unmodeled searches patterns. So we learned from the gravitational wave detection team that the current telescopes work primarily with existing templates. And all of those templates, and I think Lyana showed that, are based on Einstein's relativity theory, right? So we know from Einstein's relativity theory that the signals should look like this. In our world, we don't know how the signal looks like. But we do know that there are patterns. And one of the things that on financial markets we look for patterns is a technique from Japan called Japanese candlesticks. So that's why we decided to focus on Japanese candlesticks, because a lot of manual traders actually look at Japanese candlesticks to, so the typical traders manual traders in a trading room, they look at charts like this to actually make trades. So we thought, okay, let's, in our case, we don't have Einstein's relativity theory on financial markets, so we take Japanese candlesticks to replace that. And what we also wanted to do, and that's also a similar challenge that the Einstein team has, we don't know how long the frequency of the signal is, right? So some patterns could be, 1 microsecond, some patterns could be 1 second, some patterns could be 4 hours, or some patterns could be a month. We don't know. So one of the things we would like to do is search on multiple time frames. Because if we only look at one time frame, you're less likely to find signals, or you only find specific signals. But if we look on a lot of different time frames, we might be able to confirm signals or get better quality signals from that. And what we also decided to look at is different types of time frames. So for example, let's take a 1 hour time frame. The definition of 1 hour is basically random, right? Because what is 1 hour? 1 hour is a differentiation in time. But in the time slot from 1 to 2 hours, we could trade 1 million Bitcoin. And in the time frame from 2 hours to 3 hours, it could be 100,000 Bitcoin. So you have different volumes. So the data is not comparable, right? You compare apples with pears. So one of the things we are also looking at is to convert time frequency data into, for example, dollar volume data. So we make new time bars which have the same level of dollar volume, so that we can try to compare apples with apples. And we make a sort of a matrix and then search in the matrix for patterns. And one of the new things we want to start with in September is a technique called explainable algorithmic trading, which is a relatively new technique. We have a very good person on that who has some good ideas on that. And you see that a little bit here. Well, we're building AI algorithms, right? So we don't know why that algorithm made a specific choice. And I think it's good for us if we learn also why it made it. So that's why we want to have explainable AI. And to have a visualization of this, like, okay, what kind of signal did it actually find to come to a specific conclusion? Those are some of the things we are working on. I actually did develop already a trading bot end of last year, which we put live already on the bots platform and on our own platform. And this is not based on one of the previous two slides that some of the new techniques that we're working on, because that takes probably a year to actually work them out. But here we used, one of the things I was thinking, relativity theory, right? And what we see in the crypto market is if Bitcoin moves, all the other coins also move, right? So there's a lot of interrelationships. So one of the trading algorithms I made basically on interrelationships. Relativity theory, yeah. Everything is relative to each other, right? If stock markets go down, crypto goes down, everything is related to each other. That was a little bit what I was going to show today. And I think if everybody is interested in this topic, in November we'll have one of the people working in more detail on one of these topics to go a little bit more into detail in any of these topics. Thanks.
Thank you very much, Roy. Are there any questions for Roy? Yes.
Hey, so this is it's very promising, all this stuff, looking at discrepancies between markets, and just say if it's very successful and a lot of financial institutions start to notice and decided to try something similar, and they all came out like big trading companies and they got all their trading bots to look at these discrepancies. And then, at that point, it might have an effect on the market. So you think this type of approach of trying to take advantage of discrepancies in trading platforms, would that have a stabilizing effect on the markets? Would it stabilize the companies or make it more volatile?
I've been now active in financial trading for more than 10 years with algorithms. I've learned one thing. There's a lot of marketing in the financial industry. There's more marketing than content and reality. And a lot of players pretend like they have very complex algorithms. But if you look at the charts, only 5% actually beat the markets. So it's more sales and marketing than reality. And so I'm not so afraid about that. What we see actually with the data that we got is we found differences of 0.5%, 1% on specific coins that are there for more than 5 or 10 minutes. Everybody in this world thinks, okay, high frequency trading algorithms, within 1 millisecond the difference is gone, right? That's not the case. Those differences exist for 10 minutes, 30 minutes. So even for amateurs, it's easy to find them, right? So the market is not that advanced as everybody thinks. Yeah.
Thank you. More questions.
So you mentioned Teradata, right? So a terabyte of data. Is it possible within the Einstein Telescope project to have a sample to try some of the algorithms that we are trying on a different context of this data, or is currently proprietary and you prefer not to share?
You mean you want a financial data set, basically? Yeah? Yeah, we have plenty of data, so we can send you a financial data set. You can try some of the algorithms. So that's always possible, yeah.
One more question?
I was curious about the Japanese candlesticks, and I didn't really get it. You pointed to this figure, but can you explain what is there? Because you said that's what everybody uses, so sounds like a useful thing to learn.
This is This is a technique from an area called technical analysis that was developed roughly 30 years ago when I was still a teenage person. I was still trading, and this was considered to be in the financial industry as not serious, basically. But nowadays it's basically used by all the manual traders. This was developed by somebody from Japan. I actually don't know. I think it was a professor actually from Japan. And so when the bar is green, you know, it went up. When the bar is red, it went down, and then you see this is the high of the day. This is the high of the bar. This is the low of the bar. Opening and close. It's a very simple methodology, but the patterns are. People try to recognize patterns in the sequence of the bars. So sometimes you have a head and shoulder, which means you have a trend like this. And a head and shoulder is typically considered to be a very strong signal that the market will go down. And you also have a similar bottom signal, basically. So there is literally hundreds of different signals, you know, based on 3 or 4 bars that could exist, basically.
So X is time and Y is the value of what?
X is time and Y is the price. Yeah.
So if you have a head and shoulder that happens in 5 minutes, or if it happens in 5 hours, that has a different effect.
On any time bar that you want.
Okay. And basically there you're using a convolutional neural network to highlight the bars.
It gets a little bit more complex. This gets the question is, are you using a convolutional neural network to actually? Yeah. So there's a strange idea behind this. And the strange idea, we have a lot of strange ideas. The strange idea is a human person could, we all know, you know, if you see a visual picture in front of you, you tend to recognize a pattern better than if you look at a series of numbers, right? Like an Excel spreadsheet. It's the same data, right? It's visual or it's a series of numbers. So our thought was, would it be the same for an AI model? Why did we ask that question? Because an AI model, AI technology is actually built to replicate the neurons in the human brain, right? So if that would be the case for humans, that visual information is more easily interpretable than a series of numbers, why wouldn't it be the case for artificial intelligence? So one of the things we have been trying is that we run the AI models not on the data, but on the graphical representation of the data, and then use convolutional neural networks to actually recognize the pattern. So we don't look to the real data. We first translate it into the image, and then try to recognize the pattern from the image. Yeah. So we have been trying that for the last year already with some tests. It does look to work better, but we didn't manage to. It does lead to a higher, if we do the unit test, it does lead to a higher accuracy than running it on the data. So it seems to work, but we could not convert it yet into a successful trading algorithm. So that's the step we're still looking at. That is a little bit more complex than we thought, apparently. Yeah.
Thanks. One more question.
Yeah, we are talking about valorization. I'm really curious to hear about what insights and results can you already define maybe from this collaboration, because you are comparing with gravitational waves, and I was just curious, you had this slide where you said why it was interesting, but I'm also curious to see what if you already have some benefits for your company.
Yeah. So this we have 2 teams, right, as part of this collaboration. This one is too early to say. We're just testing and building, and it's not working yet. This one, we had Gregors had the first test this week. He thought he was getting 30% return per month, which is very good, obviously. So I told him I don't believe it. Check your data. He checked it, and the assumptions were not completely correct everywhere. So he's still testing. But this I think this one looks promising. This one, not sure yet.
And you wouldn't have this. You wouldn't have this if not for this collaboration. Is that
Yeah, more or less. These type of algorithms take 1.5 to 2 years to build, just for one algorithm. It would have been easier for us to just take one of the existing algorithms, copy paste, make some changes, right? So these are quite big investments to do. And they're also based on the idea to combine what is typically happening when we look at data from multiple exchanges. We just look to the differences and trade on the differences. That's quite easy. But the idea, the new idea basically here is, can we combine the signals from the 3 exchanges to create a new data set, which is higher resolution without local noise? That is something, that idea I got from this collaboration, which otherwise I haven't seen that before yet, so yeah.
How much time does it take to do that calculation? So how much are you behind the market by combining this? Or you can do that in milliseconds as well.
You mean the actual backtest? Yes. It depends on the data. If I run it on 5-minute data, 1-minute data, tick data, I think Gregor, you are running on tick data, which is huge. That's probably takes. Yeah, but we also converting that to yeah. Yeah. But this could take 2 days on one simple backtest. It could be, but we have 2 supercomputers actually. We actually build our own supercomputers to run these models. So this can get quite advanced and quite expensive in terms of compute power. Yeah.
All right, Roy, thank you very much for sharing this with us. Thank you. So, and with that, we are at the end of our event today. So this was the first event in a series of 4. Some of them will be a little bit more technical, as we have already revealed. So in November, it will be a quite in-depth discussion. And then next year, we have 2 other events where we will again update you about what is going on in the Einstein Telescope Technology Project. I would like to thank our financial partners. So we receive funding for this project from the European Regional Development Fund, from the European Union, and from the Ministry of Academic Affairs and Climate, and from the province of Limburg via the OPI-Zuid React EU program. So thank you very much for coming, all of you here and all of you listening in online. I hope that you learned something. I did. So let's see what we can learn together in the next events. And I hope to see you back. Thank you.